So we're going to consider an example of type 1 and type 2 errors and do some calculations. So here's a problem. Here are two hypotheses, and let me explain what they mean. So HO is that mu is equal to 40, and HA is that mu is greater than 40. And mu is equal to the average sales per catalog. And what we're describing is this. This problem describes there's a person who has a company where they mail catalogs out to thousands and thousands of people. And the catalogs have pictures of things that they can buy, maybe candles, clothes, toys, you name it, all different kinds of things in this catalog. This used to be a pretty popular way to sell things. It still happens today, but most things happen on websites now, and people don't waste the money to spend catalogs. Okay? Now, here's what the person who runs the company believes. He wants to see if you redesign the cover of the catalog, whether or not sales will increase. Okay, so a very large number of customers will receive the original catalog, and then a random sample of customers will see run with a new cover. And the new cover might be prettier to look at, have nicer pictures. And this guy's thought is, hey, if we have a nicer cover, then people probably open a catalog and more likely to buy more than the average of $40 worth of stuff. Okay? They go on to tell us that the new cover catalog was sent to 1,000 people, and that the standard deviation of sales of all the catalogs is known to be $60. Okay, so you should make a note of that. If sigma is equal to 60, then that implies that we're going to have a z-test. And since there's only one sample, you know it's a one sample z-test. So you should identify that right away, whether it's a one sample z-test or t-test. If we didn't know sigma, it would have been a t-test. Okay, so lastly, they do give us an alpha level. The person's going to use alpha level 0.01. Let's describe a type 1 error in this situation. So if you made a type 1 error, then that means you rejected HO in favor of HA, but HO was true. So that's what it means. Now in this case, this person would have rejected that the sales were equal to $40. They would have rejected that HO, and they would have thought, they're thinking this. They're thinking that mu is greater than 40 with the new cover. That's what this person is suspecting. Well, if they're suspecting that mu is greater than 40 with the new cover, then they're probably going to spend the money to get a whole bunch of brand new catalogs, right? And so, you know, if it costs a few dollars to make a new catalog and they send out 100,000 catalogs, so about a couple $100,000 this person might spend to mail out all new catalogs, thinking that the mean sales is going to go up, right? Because they made a type 1 error. But in fact, this is true. So this is actually a really bad thing. This person's going to spend a lot of extra money to get brand new catalogs to mail out, and it's not going to make any difference in the average sales. So the effect would have just could have left the catalog alone and kept the money they would have spent buying new catalogs. All right, and if we were interested in the probability of a type 1 error, we showed or explained that it's simply equal to the alpha level, in this case 0.01. Okay? Because this person insisted on such a high alpha level, it's very unlikely, right, that they'll make a type 1 error. And if you think about it, that's probably a good idea for this person who owns the catalog. This person is going to want to be really sure. They're going to want a really significant result, or a very, very small p-value, before they decide to invest in redoing all their catalogs. So this is an example of a situation where instead of using alpha equals 0.05, you might want to use 0.01 or something even smaller. Okay. All right. Let's move on to type 2 errors. So a type 2 error occurred. Let's think about what you did. That means you accepted HO, or you failed to reject it, but HO is false. So in our case, the person would have done this. They would have accepted the fact that the average sales with the new cover is still $40. But in fact, that was false, and this was true. In fact, with the new cover, the average sales would be greater than $40. So let's think about the consequences for this person. What would they do? Well, if they thought that, hold on a second. Yeah, they accepted this. So if they accepted that, then they would not buy new catalogs. And if they didn't buy new catalogs, then that would mean that they would miss out on higher sales numbers. So that would be the consequence for a type 2 error in this problem. Now, when I look at this these two types of errors I could make, I think I'd rather make a type 2 error. A type 2 error means I wouldn't have bought the new catalog. I would have missed out on some extra sales, but at least I didn't spend all that, I just missed out on something. In the other case, I would have spent money to buy more catalogs and not seen any increase of sales, so that would have been a definite loss for me. So a type 2 error is probably the less severe of the two errors. All right, so let's actually calculate the probability of a type 2 error. Now, this is the hard of the two probabilities to calculate because you can't do it unless you're told the true mean. So we're going to calculate the probability of a type 2 error if the true mean is 49. Okay? So in other words, we're going to find the probability that we accept HO, that mu is equal to $40 in sales, when in fact, with the new cover, the new sales rate per catalog would be $49. Okay? And that has to be told to you. You won't be able to guess what the true mean is. The problem will say, find the probability of type 2 error if mu equals some number. The way to do this correctly, think of it in steps. The first step is find your acceptance region. You have to remember, if you made a type 2 error, then that means you accepted HO. Okay? So let's draw a picture. First off, our HO is that mu equals 40. And our HA is that mu is greater than 40. Okay? So we're going to find the region on which we would have accepted HO, because we know that's what we did. So here's the normal distribution. Here's mu equals 40 in the middle. And if we accepted, then that means we didn't get less than alpha equals 0.01. Right? We would have needed a p-value less than alpha equals 0.01 to reject. So I'm going to shade in that p-value over here. There it is. There's the p-value. And what I know now is this, that there's some x bar here. And I don't know it yet, but I'm going to find it. And the following is true. If x bar is less than whatever that number is, then we would have accepted HO, that mu equals 40. If I had an x bar over here somewhere, then my p-value would have been all that area, which is clearly bigger than the red alpha equals 0.01. So any x bar over in this region would have been an x bar where I would have accepted HO. And since I'm making a type 2 error, I know my x bar is less than this magic number, whatever it is. Now, the question you want to ask yourself is, how do you find that number? Here's my first claim. You know the z-score that goes with it. So what we're going to do is, we're going to look up an area of 0.99 using inverse norm. Remember, inverse norm is based off area to the left. So you do second distributions. Oh, hold on a second there. Number 3, which is inverse norm. You use inverse norm whenever you know the area to the left of the z-score that you want. So you type in 0.99, comma 0, comma 1. All right? And if you do 0 and 1 for the mean and standard deviation, it'll give you back a z-score. We hit enter. Okay? And there we go. 2.326. So that's the z-score that goes with this. 2.326. All right. Well, let's think about z-scores for a moment. Z equals x bar minus mu over sigma over the square root of n. And that's the case for a z-score in a significance test. And if you think about it, in this problem, we actually know all the pieces. So you actually can fill all this stuff in. 2.326 equals x bar, which I'm looking for, so I'm not surprised I don't know that, minus mu over 60 divided by the square root of 1,000. And that's just all the things we were told in the problem. So we're going to be able to find that x bar that goes in our acceptance region. So now, I'd like to solve this. And you can do that by cross-multiplying and adding and so forth. But you can do something else in the calculator that's kind of nice to solve that. Here's what you do. You go back to the inverse norm key. You do second distributions number 3 inverse norm. And you just type 0.99, comma, the mean, which are going to make 40 now, comma, 60 divided by the square root of 1,000. So what you'll notice is I never typed in the z-score, but I don't have to, because when I do inverse norm, the calculator finds the z-score for me. So you type in the area to the left, the mean, and the standard deviation, and you hit enter, and there it is, 44.41. So if you take the time to solve this by hand, you're going to get x bar equals 44.41. Okay. Now let's think about the meaning of this number. So the meaning of this 44.41 is that's the cutoff. 44.41 is the x bar that would land me exactly in this location. And if I had gotten beyond that, then my area would be less than 0.01 and I would have rejected HO. If I got less than that number, if I was less than this, then I would have been in here somewhere and I would have accepted HO. And we know that happened because I made a type 2 error. So what we can say is if x bar is less than 44.41, then we accepted HO. So that's the end of step 1. Step 1 was to find what's called your acceptance region. Okay. Now step 2 is pretty easy. Now we just go and find the probability of a type 2 error. And here's what you need to remember. When you're asked to do the probability of a type 2 error, they'll always tell you if mu equals, and they'll give you what they're calling the true mean. So here's what I know happened. I know that when I did my significance test, I got an x bar that was less than 44.41. But in fact, the true distribution I was working with had mu equal to 49, not mu equal to 40. So I'm going to draw a new normal distribution. Here's what I do. I draw a new normal distribution with mu equals 49 in the middle. And then I mark off the x bar, which equals 44.41. And if I accepted, then I know already that mu was, or x bar was less than that. So I just shade in that area. And that is the probability of my type 2 error. So let's finish off. So we can go to the calculator. And this time we want area. So it's not an inverse norm. It's just normal distribution, or normal CDF, number 2. Okay? And if we think about our picture, our area is going really far down to the left. So this is some very negative number up to 44.41. So that's what we're going to do. Negative 1, there's a lot of zeros, comma, 44.41, comma, the true mean, which is 49, comma, 60 divided by the square root of 1,000. And that's another fun thing to keep in mind. The standard deviation, you don't change that. That stays the same. Okay? We close the parenthesis, and we hit enter. And there we go. We get a very small probability. And actually, that's really good. So the probability of a type 2 error in this case is 0.0077. Okay? So now, let's interpret that type 2 error. So this type 2 error is saying the following, that the probability we accept HO, that mu is equal to 40, when the true mean is mu equals 49, is 0.007, or about 0.7%. So we would say it's extremely unlikely to make a type 2 error in this case. All right? Now that should sort of make sense to you, because if we were testing the hypotheses that mu is equal to 40, and our acceptance region is this number, that x bar is 44.41 or less, so we have to be in there. And then, like I said, some all-knowing person comes along and says, hey, wait a minute, no, the true mean is out here, it's 49. Then you can see how hard would it be to get all the way down here to 44.41 or less if the true mean is 49. It's very unlikely, which is why it's very unlikely to make a type 2 error in this case. Now, there's one more definition you need to know, and this is just as important as type 2 error. First off, I'll say this, that often your textbooks or different textbooks will say the probability of a type 2 error is equal to beta. They'll use the letter beta for that. Okay? Beta is not always the same. It's not like alpha where it's just 0.01 or 0.05. The second thing you need to know is something called power. And power is always equal to 1 minus the probability of a type 2 error. Or it's always equal to 1 minus beta. You'll see that in multiple choice questions. In our case, the power against mu equals 49 is equal to 1 minus 0.007, or 99.3%. So the meaning of that is as follows, that our test, our significance test, is 99.3% of the time will reject the HO that mu equals 40 when the true mean is mu equals 49. So this is what we call a very powerful test. It is very likely to detect, or to, we should say, reject HO when the true mean is 49.